Okay, so anyway, I wanted to go through heat capacity. Some of these were some. There's this kind of three parts to heat capacity. So you have the gases. That might be where you've seen before. That's from like, I don't know, chemistry, like Chem 101 or something. And then Dulong fatigue, which is the heat capacity is 3R, molar heat capacity. And then Einstein, and then divide. So I want to go through these three today, and then maybe next week the divide part. Anyway, so the heat capacity, I already went through a little bit about heat capacity. So basically, if you take the expression for enthalpy, so the change in enthalpies, VDP, TDS. Then if you're at constant pressure, the VDP goes to 0, and we have the heat capacities. DHDT is DS is defined as dQ by T, and then if you substitute that in, you get that DH is dQ, dQ dt becomes DH dt at constant pressure. So we did that. I already talked about that before. And for constant volume, do the same thing with internal energy. So du's dP, PDV minus PDV, TDS, and then a constant volume, the PDV part goes away and just have the same thing, TDS, which is dQ. So du dt, a constant V is the heat capacity, a constant volume, CV. So it's like this guy and that guy. And we earlier on in chapter 1, I went through this derivation, and we got that if you want to get relate these two heat capacities, you can do it through this partial derivative equation, and we went through that. So basically, it's the thermal conductivity squared divided by the isothermal compressibility, then volume and temperature in it. Which, if you do that for an ideal gas, PV is RT, you plug that all in, you find out that CP minus CV for an ideal gas is R. And then, so if you take a monatomic gas and say this is kind of from chemistry 101, but 1/2 mv squared is the energy, and that's also KT 3/2. That's also for each translational motion is 1/2 KT from quantum mechanics. And then there's 3 transit XYZ, so it's 3/2 KT equal 1/2 mv squared, and that also equals energy. So if you do the derivative of energy with respect to temperature for CV, then you get 3/2 R for CV for monatomic gas. If you in every kind of motion that you put into, or vibration or motion that you put into the atom, you get another R to this. So you keep adding R's to the 3/2 to get, like if you have a linear molecule that can rotate, you have one more, so it's 5/2 R for CV. Nonlinear that can rotate and also has can rotate in 3 axes for nonlinear. The 6/2, you have another R for the other motion. And then for every vibration, you add another one too. So depending on how you break down the vibrations of the molecule, which have to do with this 3n minus 6 vibrations. So you can add up, make a list for every kind of gas that you could have. You can get the heat capacity, and CP is just R more than the CV. So it's kind of a simple model for gases. So that's not really what we're interested in. We're interested in this. This is a picture of some gases showing how this heat capacity works. So there's no. So this is just be 3/2. R. So 3R is 25 joules. And then if you do 3/2 R or 5/2 R for this hydrogen, you get 20.8 because it's CP, not CV. So 3/2 plus 1 R would be 5/2, and you get that value, and it's just what it is. So you can predict the heat capacities for gases. So as you go, if you start out, so these things you added in here. So you have like rotational motion, translational motion, which happens all for any temperature. Rotational motion is a little bit higher energy, so at a higher temperature. And then vibrational is a higher energy still, so it comes at another temperature. So if you look at the temperature dependence, you have this 3 translational, so that would be the 3/2 R value, and then rotational kicks in at some temperature, and then vibrational later. Right, so that's basically what you see is kind of this kind of ski slope thing with multiple hills on it, right, for the heat capacity, the function of temperature for gases. So if you go to solids, you get Dulong-Petit law was proposed in the 1800s. So this is for solids, and it basically says that the heat capacity, the CV is going to be 3R, right? And then if you want to get CP, this simple ideal gas thing won't work. It isn't just R. You have to know what the actual temperature dependence of the thermal conductivity and the compressibility are to figure out what CP is. CP, you can kind of calculate. CP is going to be more involved. Like you have to get an expression for this thing. So it's basically empirical expressions to take care of this difference, right? So things get a little bit dicier once you get away from ideal situation, but nonetheless, there's this idea that if you have a crystal, so a crystal, so then at this point you have to think about models for what a crystal is going to be. So crystals will be like the simplest thing to consider. All right. So you have a crystal. And then you can think that the atoms could be like thought of as kind of a spring plucking together the atoms. You have like that the force is going to be kx, and the energy is going to be kx squared by 2 because it's an integral of that. So it's like du equals f dx and things. You want to get the energy, call that u. Right. So basically, you can look at crystal like that, and then you would say that you just have this. You have these 3 vibrational modes associated. Say it's a 3D crystal. So you have X, Y, Z, and you have 3 springs holding it together. And you would have each has a kinetic term and a potential term. So when a spring vibrates, it's going to follow like a sine wave, a sine of the of time, say. And so the spring's vibrating, so it's got 0 potential energy there, but here it's got like kx, if that's x, this is distance, this is time, right? So basically you have a potential energy, and here you have maximum kinetic energy, which would be like 1/2 mv squared. So you have 3 degrees of freedom. There's 2 kinds of energy that you add together. Each energy is going to get 1/2 kT from quantum mechanics. So you're going to end up with 2 times 3 would be 3 times kT, or if it's in moles, 3R. So that's kind of like the motion of each atom in 3 dimensions, 2 kinds of motion, kinetic and potential. So that's like 1887 or something, I think, the date on that was figured out. So you get 3R, and then you look at the data for materials, and like, yeah, that's kind of the 3R. So 25 joules per mole Kelvin is 3R. So that's basically, a lot of things are close to that. This goes from like, this isn't a full scale, so it's going from 23 to 30, but basically most things are following that 3R rule at room temperature. Right, so that seems pretty good. And here's some things with strong bonds or like deviate from it slightly, but it isn't. Basically 3R is a pretty good shot for CV for like most things, most crystalline materials. Right, so that's the first of these 3. That's called the Dulong-Petit law, right? So, and that up until like 1880 something, 85, was this Boltzmann thing. Then so I guess 20 or 30 years later, 1905 is like Einstein's business, or 1877. It's kind of like 30, 40 years later. Einstein, and this was kind of elaborated on, like what is U for this? So you plug in like the position of the atom. It's a spring, so it's bouncing back and forth with a sine wave. It's a sign of the frequency of the vibration. So what is the frequency? Well, you balance out the kinetic and the potential energy. So if you have a spring, in the midpoint, it has no potential energy, and at the high point, it has all. So it converts from kinetic to potential. They have to be equal to each other. So you set up that differential equation, plug in that it's a sine wave for x, and you solve it, and you find out that the frequency's the modulus by the mass, which means that the frequency of vibration. So if you want to measure the modulus, this is a spring constant, but it's like a modulus if you do it per mole. Then basically you can get the modulus from the frequency of the vibration if you know the mass of the atoms in the crystal. Right, so that's kind of a nice trick to do, like from a vibrational analysis of the material, or from measuring the heat capacity, because the energy is a derivative of internal energy. From measuring the heat capacity, then it connects it with this modulus. So somehow two things that seem to have nothing to do with each other are connected, like a mechanical property and this thermal property are tied together, right? And within this model of springs, a bunch of springs, right? So that's like, I think Boltzmann originally just said 3R, but Dulong-Petit said the 3R in the mid 1800s, and Boltzmann came up with this idea of the springs later on, 1877. So, and that in this kind of frequency analysis of the thing. So anyway, so then you have to think about something. So Einstein came along with a different idea on this. See, what's this business? So Einstein came with this idea that it's not a spring like that. It's a spring like a guitar string. So the guitar string has like a tone, like the E string, right? And then it's going to have these overtones too. So it's not just like, if it was a computer sound, it would be E. It would be like what you hear from a computer when you say play E. It's like, when you play guitar string, it's like got a lot more richness to it, right? So it's got these modes of vibration, right? So n equals 0, n equals 1. And then you can have like 3 vibrations in it, and you can break it up into any, and they always have to end at 0 here. There'll be all these other frequencies, but the frequency of each is going to be an integer. It's going to be dividing the it's going to be higher and higher frequency, so higher and higher energy, and it's going to be n times the frequency, right? So the first order is the lowest energy, and then you're going to have all these higher energy states to it. So this is what Einstein did. He said it's like, it's not just a spring, it's like a guitar string, it's got modes to it, right? And this becomes a little bit different issue, right? So then you're going to have like not one energy to it. You're going to have a series you have to sum. Like you have to sum over all these modes of vibration to get the energy, and then take the derivative energy and get the heat capacity. That's kind of like the thing. Now the twist of this. So at the time quantum mechanics was invented, and this idea that if you go to absolute 0, it can't, like say an electron or any kind of subatomic particle, you can't know the energy. You can't have like energy 0 at 0 degrees Kelvin, because that would mean that the quantum particles, you would know both their position and their velocity. Position would be wherever, and the velocity would be 0. And that can't be, because that's Heisenberg's uncertainty principle. You can never know the position of anything. If you know its velocity or you know its position, you can't know both. So that would break that. So you have to have a 0-point energy. Then experimentalists measured it. So it was like 1/2 h nu is a 0-point energy for the thing. So you have the modes, and there's a 0-point energy they have to add into this. So E is h nu times 1/2 plus n, and it's an integer from 0 to, it keeps going up. Like you have all those other modes of vibration and the thing. So anyway, so then so along that line, so this is kind of I think this is the last thing Einstein did. Basically, you can say it first because you have the Dulong Petit that's 3R. So how do you fit that in with this picture, right? So you say the Helmholtz free energy. So it's going to be this 0 point energy times the number of atoms, n's the number of atoms, and let's say in a mole or in whatever you're looking at, and then plus the sum of all these modes of vibration. So the vibrations are new, so it's like n times nu zero would be each of these, and n would be I here. So you can sum over all the modes of vibration that goes from 0 to whatever, the top number, infinity. Right, so you have a kind of an infinite series. And then each one's going to have this KT energy with it. So you have like n for the ground state, n times this total summation. That total summation ends up being like called an Einstein frequency, like an average frequency for the material. So it's that sum of all those divided by the number of modes, or like the degrees of freedom, XYZ. The G would be 3. So anyway, so you have that, and then if you write du is PdV TdS, or no, let's see, no, U is going to be AT minus TS, A plus TS. U is A, let's see, U should be A, or let's see, A is U minus TS, U is A plus TS. That should be, oh here, plus TS. And then dA is minus S dt plus minus PdV. Right? So that's that thing, the derivative part, just from the thermodynamic square. Right. So then dA dt, this goes to 1, and then you just have minus S, and then PdV, and then so dA ds is minus S, so you can plug in dA dt is minus S, so you can plug in dA dt for S, and you get this expression for U. Because you have an expression for A, you can just do a derivative of it. First term doesn't have any T, and then this term has this T in it, so derivative of first times the second, and then derivative of the second times the first, using this rule that the derivative of a log of x is the same as saying dx by x. So you can substitute in that derivative basically for minus 1 over t if you figure it out. Right. So you can get an expression for that. You have an expression for A, you can plug it in and get an expression for U based on this idea of summing up these frequencies of the different modes. So you have like any, and you find out these two terms cancel, like the sum drops out. And then you just have sum I of NKT, which ends up being just the number of modes times NKT. And then that's basically G is 3 degrees of freedom, and they just get Dulong Petit's rule from that. So it's possible to take this Einstein thing, get the same answer that you get for the spring thing from Boltzmann. Right, that's kind of step one. So that means it's going to agree at the high end. Like if you plot it out, this will be 3R at the end of this thing. So you'll get the normal Dulong Petit result from this thing at the high temperature end. At the low temperature end, this thing gets more complicated. So the Einstein approach gives you the answer of Dulong Petit, but it can also like explain. So this is a temperature dependence for this aluminum silicate crystal. It shows like it's plateauing at the high end, but the heat capacity drops when you get to very low temperatures. It's like it goes to almost 0 when you get to absolute 0. Right. So there's a dependence that doesn't exist in the Dulong Petit. Dulong Petit is just like a straight line here. It doesn't have a temperature dependence. So this is because the modes of vibration have different energies across the spectrum of all these different modes of vibration. So the higher the number, so these little teeny ones have a really high energy. So nu is high, E is H nu, so the energy is high for those, and like energy is low for the big one. Right. So and energy is also KT. So as you drop the temperature, you're exciting fewer and fewer of the high energy modes. And you're just going to end up with the one mode left. And so So basically you have to figure out the temperature dependence of the contributions of these modes. And that's basically the Einstein model for the heat capacity. Right. So anyway, so energy of one harmonic oscillator is h nu, the ground state, plus h nu times n, and then n zeroed to infinity integers, and then so this comes up to present. So Einstein kind of invented, I guess he invented this partition function in this case, which is called the Zustan sum, which means the sum of all the probabilities, kind of Boltzmann probabilities. So each energy divided by kT, so this would be a Boltzmann probability, like energy by kT exponentially gives you a probability of that state. Right? Same thing as so it's basically the Boltzmann thing was like E over KT is the probability of the state, whatever the state is, right? So it means like the like log of the probability is going to give you like log of the probability times KT gives you energy. And so it's just that's kind of our normal expression for entropic, for calculating the entropy. So an entropic system, thermally driven system. Right, so you just sum up all those, you get a number. Like, so that's a number that you would like normalize by. If you wanted to get the probability of one of the states, you take the probability of that state. You're going to get the energy for one state. You take the probability of that state times the overall energy divided by the Zustan sum, right? Sum of the states, and then basically that would give you the energy for that state. So every time you want to get an average in this kind of scheme of these moments of energies, you take this number times the energy times the thing that you want to average, and you divide by z, which is the sum of the probabilities. Right? So that's just a normalization factor. But it turns out log of this thing is the energy of the system. Like we'll find that out. But basically, so this is sum, or the partition function becomes a thing that governs how you calculate the energy, even though it looks like it's just a normalization factor. Like the sum of all the probabilities would be like how you normalize something if you're trying to calculate. But anyway, so you plug in what the energy is, and then you get this expression for this Zustan sum, the Zustan sum, right? And then so if you take this, so the sum of geometric means that if you sum to infinity, from 0 to infinity, x to the n, you get 1 over 1 minus x. So you have that kind of an argument here, like the sum of this thing, and n is the argument. So you basically have this thing. So you can just you can get rid of the sum, and you can just say, this is going to be 1 minus e to the x that you had there, and then the top is going to be the zero state one, that x to the 1/2 is from the zero state energy. If you don't have the zero state energy, this thing becomes 1 over 1 minus e to the minus x. So in some books, you see this thing, where they haven't included the zero state. Some books, you see this thing, but they're both talking about the same thing, kind of. Right? So if you don't include the zero state, you get this. Some of the books show that. Most books are showing this thing, which includes the zero state energy, this 1/2 thing. So anyway, this partition function becomes like one of the main things you need to know about and looking at this, like that this exists. It's a simple idea. It's just like a sum of the probabilities. I mean, so it's a normalization factor, but it ends up, because you'll find out that the log of this gives the energy. This becomes the thing you have to calculate whenever you want to do a thermodynamic calculation of atomic-based systems. So this becomes the main topic of everything, even though it's just a normalization factor. So anyway, have you guys ever heard of partition function before? I mean, it's kind of like it becomes like the main topic in certain areas, and then like other places you would never hear of it. So it's kind of a thing. Anyway, there it is. So you have to kind of get used to it somehow. Don't think it's anything mysterious. I guess it's just the sum of all the probabilities. So if you want to get the probability of something, do this Boltzmann factor, but it's not normalized. So you have to normalize it by the sum of all the things. So it would be, so the thing, like say So you got 50 for this, but the sum of them is 500. And your 50 is really 10%. Like if so this thing doesn't have units, so you have to have some way to convert it to 0 to 1. And this is the normalization factor that would do that. Sum of all the possibilities you could get, then that would be the thing you'd normalize each one by to get the percent that it is, or fraction that it is. Right. So anyways, that said, so you can get the average energy. So if you want to, like, say you want to get the average anything, you would take your thing and then multiply it by its probability, which is this Boltzmann factor. So X here is like 1 over the temperature, right? And then in each of our frequencies is n times the frequency. If you collect all the parameters into this X, it's h nu over kt times n gives you the energy of that mode of vibration that's going on. So, and then if you know the energy of that mode of vibration times the probability and then normalized by the partition function gives you and you sum over all the possible energies, that gives you the average energy. That's how you calculate an average. You take the number for that state times the probability divided by the normalization factor, and that gives you the average of it, right? So this thing has so you know that the z is the sum of these states, right? So if you take the derivative of this, you take the derivative of this with respect to beta, which is 1 over kt, then you'll find out the derivative of this with respect to beta, so you get energy out front, beta drops out. The derivative exponential is exponential, and then exponential times the derivative of the argument, which would be minus beta in this case, derivative of the argument. So, and then if you're driving with respect to beta, you get the energy out front, negative energy. So that's where you have the energy, except there's a negative missing, so you pop that in. So this is derivative of z with respect to beta, this thing. So this is what Einstein did. He did that math trick, and he said, like, oh, I remember this, dz by z is d ln of z. So yeah, you can pop that in too. So you pop that in, and then you figure out what that derivative d ln of z from this expression, and you get this expression. And you figure out that if you divide by e to the minus beta hv, then e to the plus beta h nu minus 1. So you end up with this term, and then h nu is out front, and you just get that expression for the energy. So that's the Einstein energy, and this thing's called the Bose-Einstein. This term 1 over this thing is called the Bose-Einstein probability. So the probability of a state. So h nu e times that 1 over that thing is the energy by the Einstein model, this kind of guitar string model. And 1 over this thing is called the Bose-Einstein probability. So you want to know the probability of finding a given state, say of electrons of a certain energy. When you plug in 1 over e to the h nu of the electron kt minus 1 gives you the probability of finding that electron of that energy. This comes up later because if you want to know the conductivity of a metal, right, then you're going to have to sum up the Bose-Einstein probabilities of finding an electron, because the conductivity is going to come from the available electrons at that energy. So if you want to know the temperature dependence of conductivity, it's going to be proportional to the 1 over this thing. So these things are all linked together. Like once you start in with the guitar string, you figure out you're going to have to do the summation, and then you can start answering, like, how does the conductivity of a metal change with temperature? Like kind of things you wouldn't think are connected to it. So that's why it becomes one of the things that Einstein did. He did a bunch of things, but this is one of the things that's like seemed like hard to do. But when you look back on it, if you whittle through this, it's kind of like makes sense, hopefully. The stuff, like you see it once, you'll have to see it a few times. I mean, this is something that you can get with one shot. All right, so once you have the energy of this guitar string with all the modes, all you need to do is take a derivative of it with respect to temperature. And each of these, remember, x is 1 over 10, x has 1 over t in it because beta is 1 over kt. So you have to take the derivative of this thing, which ends up being a little bit of a mess, but not too bad. And then the derivative eventually gives you this expression, which is Einstein. See, this is for one atom, and there's 3 modes of one motion, like one guitar string, and there's three XYZ. So 3 times that gives you this thing, which is the Einstein heat capacity. So it looks a little bulky if you collect together everything that isn't. So if you collect together beta H nu E into a thing called, because it's going to have units of temperature. So you take the temperature out of beta and you have the H nu E. So H nu E over K. And then you have 1 over T left. And this thing would have H nu E over K would have units of temperature. So you call that the Einstein temperature for the material. So every heat capacity that you have for Einstein, for every material, you're going to have a distinct Einstein temperature that defines basically how you calculate the heat capacity. So it turns out like the higher that number is, so that it'll be typically like 300K or 200K, something like that. So room temperature-ish, right? So, and that's for a normal metal that has strong bonds in it. The bonds get weaker, that temperature drops down to like 20K or something. The bond, if there's no bond, you have a free metallic atom floating around. So you have a lattice. They have a lattice that's like aluminum, like FCC. And then you put in like some other atom, and then some of the aluminum. Anyway, within that FCC lattice is some spaces somewhere where a free aluminum can stick itself in. And that thing has almost no bonds with anything. So there are some metal, I'm trying to think of the word. There's some crystals that will have spaces where an atom can fit in, where it can, they call it it's called radon. So that atom doesn't have any bonds. So that the Einstein temperature for that is going to be like 20K, like really low, like 1/10 of what it would be for something normal, right? So when that happens, so as you raise the temperature, so this thing's eating up energy as it moves. Like the motion is how it's consuming the heat that you put in. Heat capacity is how much energy you have to put in to make it raise temperature. Because it's got this motion, it can eat up a lot of energy. It's going to have a big heat capacity, right? So so there's a whole group of metal crystals that will have this kind of situation, you know. So it's interesting. All right, so it was interesting to begin with. So it would have like some high heat capacity, like a normal heat capacity of like 20, right? So this is copper. So it's got like 20 heat capacity. And it's got a 244K Einstein temperature, right? And this thing is for this aluminum silicate. It's got 200, right? So it's 10 times more heat capacity because it has some like these open aluminum atoms floating around in the crystal, right? And it also is a perfect fit to the Einstein model because the Einstein model is a single vibration, which is one guitar string, right? But in reality, the vibrations in a crystal aren't like one. So the atoms are hooked together. If I move this atom, it affects that atom, and it affects that atom, right, in a crystal. So it isn't like just, in this case, it is just one free aluminum atom, right? But in this case, if this guy moves, it affects that guy and this guy. So everything is tied together. So that's a cooperative motion, and this is an independent motion. So if you have independent motions, then you get perfect Einstein. And this is an example of a perfect Einstein, which is rare. So it does describe generally the way things look, but it doesn't really match it. And the big problem with the Einstein model is down here. And people started to get interested near absolute zero because that's where you get superconductivity. Okay, so basically people in materials and kind of the physics end of materials, we're looking at like quantum effects down in this region because they wanted to see how they could make a superconductor where there's no resistance. So you can make wires with no resistance, you know, so which still hasn't exactly reached fruition, but I mean, there's right, how you tune materials to shift that transition point up to the higher temperatures where it would be a superconductor. That's kind of one of the reasons why people are looking at such low temperatures. And also because, well, because it's kind of interesting, I guess, if you have a machine that can get you to absolute zero, then this is kind of one of the things you would look at is the heat capacity and the conductivity and some other things, right? So anyway, this all falls into place and opens up like a whole realm of people getting PhDs in this. So like nowadays, nobody is doing this, right? And for a while, so in the 1970s, like everybody was doing this. And then like in the 1980s and 90s, people started to say like, can we make wires with this for power transmission? So there was kind of an engineering thing going on to take superconductors and make them into actual transmission lines and things. And then out of that, they kind of got like NMRs, these analytic instruments that have superconductors. You cool it down with liquid helium, and then you kind of get into this temperature range where you can start to see certain effects. I'll talk about in a minute if we have time, but basically there's effects that happen when you get to such low temperature that can give you superconductivity, right? So anyway, so like I said, no one's doing this now because they found out, well, the things they could do, they did. And then basically there was nothing left to do, I think, to improve this. And that most of the engineering projects to do this, to make it into actual transmission wires and things failed. Like you couldn't do it on a large scale, right? You could do it on a small scale for something like an analytic instrument that has superconducting magnets and things in it. But basically the large scale didn't work. So anyway, it's still like, this is still like the bread and butter of materials thermal, I think, is this kind of approach to looking at, because it starts to get you to look at like phonons in the material. This is the origin of all that. So basically it's kind of a beginning of some things, even though the application part of it didn't really work out exactly. Not the way people had hoped, you know, which is true of a lot of things. Anyway, so this is our equation for the Einstein heat capacity, the CV. And then again, the CP, to get the CP from CV is a little bit empirical, like there's empirical functions to convert it. It isn't just add R to this. So basically you can calculate CV, which is pretty standard. Like theory gives you CV and experiment gives you CP, and there's always a disconnect between the two. Anyway, this is Einstein temperature. So there's an Einstein frequency, Einstein temperature, and then the CV works pretty well for a few select materials, but generally it matches up with Dulong Petit at the high end, and then it's got, you can see it's approaching 3R. You can see there's like a discrepancy, and there's a big discrepancy when you get to low temperature, which is what Debye addressed, right? So there's a thing called density of states. So if you put energy into a material, and then it's going to be distributed among all the different things that could happen, vibrations of the atoms, translation of the atoms, rotations of the atoms, those three things, I guess, right? So and then the crystal, the lattice itself can kind of vibrate, right? So you can think of, so you're going to put energy into it. So the lattice can vibrate, like you can have a propagation of a wave through the lattice, right? But it can be, that would be a transverse wave. And you can also have a longitudinal wave. The longitudinal is like sound, and transverse is the guitar string. Now it's strumming and it's vibrating up and down. Longitudinal means that there's a compression of the crystal, so the atoms actually move together more than they decompress. So the longitudinal is like sound. When sound travels through space, the air is compressed and decompressed. It's springing along like that. But it's so there's two kinds of things, like two kinds of vibrations, L and T, that are going on in this kind of crystal lattice vibrations, right? So you can see like there's a lot of different. So if you have a crystal, also there's like crystallographic directions. You have like 100, 111, 110, and then whatever 200 and everything else, right? So you have all the different directions that you have in the crystal, and each direction is going to have different vibrations, because there's different distances between the atoms and different interactions between the atoms going on too, right? So you can imagine there's like a whole slew of different things going on here, like all at once, right? So it isn't just one. Einstein's model is a little simple. Even if there's just one bond in it, even if there's only one kind of spring in it, it's still like way too simple, because the spring can have different features to it, right? In other words, it can have let's see. So we got modes of vibration. anyway, so basically, this is what Debye did. He said, instead of having one frequency that's going to vibrate, you have a spectrum of frequencies. So this is, oh yeah, this is the density of states. So you dump energy into the system. Einstein just has one kind of spring, so it's only got one frequency, the Einstein frequency. It's got one energy, so H nu is energy, so one frequency, one energy that can consume that. So as you add more and more energy, it's just going to pile up more in that frequency. So the individual vibrations going to have that energy. We can have more to accumulate more energy, but it's only going to have that one specific quantized energy. Right, so in a real material, it's got a spectrum of energies like this. So basically, there's a cutoff point. This Debye cutoff point, right? So Debye said there's a spectrum, and it's got a cutoff point, and the cutoff point is related to the Brillouin zones in the material. So if you put a higher frequency vibration into the material, if you have atoms, so the black things are atoms that are separated by a distance a, right? So the higher frequency will always be translated by the atoms into a lower frequency that has the atoms. So it doesn't matter, you can put more and higher frequency into it, but it's only going to have the effect of the low frequency. So there's a cutoff, and if you put lower frequency in, then you can have differences. So lower frequency can have differences, the higher frequency doesn't. So you have a point, a cutoff in low end of frequency, or low end, this is wavelength. So low end of wavelength, the high end of frequency, right? So basically there's a cutoff point beyond the lattice, like 1 over the A size or the A size of the lattice for wavelength. In terms of frequency or wave vector, it's going to be 2 pi over A would be a cutoff point. And after that, it just kind of repeats. If you go to higher and higher frequency, or lower and lower wavelength, or higher and higher frequency, it just translates into that A thing, right? So I'll talk about that next time, but basically that's why Debye has a cutoff at this frequency, because anything of higher frequency translates back into this frequency. So there's a cutoff point. That cutoff point is the Debye frequency, which will have a Debye temperature. So there's a Debye temperature and an Einstein temperature. Einstein would be like you have one. Debye is like you could have this spectrum, right? So the two methods, and the Debye works better. Like it's got a better matching, especially at this really low temperature. Predicts t to the -3, or t to the 3 power minus t to the power 3. So heat capacity goes with t to the 3 for the Debye. For the Einstein, in that region, it's got some exponential, it's going to be this exponential function, this exponential theta e over t dependence, and it doesn't match, like it doesn't work. Right, so the Debye fixed kind of this part that people were interested in because of something like superconductivity. Right, you can see like the two functionalities down there, and the Debye one works. So that's kind of the idea of that. And then let's see. So anyway, so there's one other contribution you need to know for the homework, which is this, that electrons, so you have the atoms and they're vibrating. And then there's also some fraction of electrons that vibrate too, but the energy is so low that you don't see, so KT is energy, so you don't see the vibration of electrons until you get to like absolute zero. Right, so when you're looking at this very low temperature region, like below 100 K, then you have to start to consider, and especially the closer you get to zero, this electron contribution, which I'll talk about at length later, but basically you need it for this paper, kind of need it for this paper. You don't exactly need it, but so it's linear in temperature. So the Debye thing's gonna go T cubed, and this thing goes T1. So if you get a small number cubed is much smaller than a small number to the 1 power. So this thing comes into play at very low temperature. If you get to high temperature, this doesn't matter. This is a T cubed term. And this thing's called the Gruner constant, that gamma. It's like in this table, it gives the Gruner constant, and it gives the Debye temperature for like the periodic table. Right? So you can kind of see how things float around. Anyway, so this is the function that gives you CV for low temperature metals, crystals, basically. right? And then that's kind of the low temperature dependence. The Debye function is more complicated than this, but an extrapolation of low temperature is T cubed. Right? And the Einstein would be an exponential, so it doesn't fit. So you can see, like in this plot, they have a plot of T squared versus Cp divided by T. So you divide by T, you get Cv by T, and then beta T squared. So that would give a straight line with beta the slope plus gamma, because you divided by T, and it intercepts gamma. So you can see this is for copper. It like matches perfectly with the Debye if you add in this electronic thing, which effectively shifts it from 0 to some value out here, this electronic contribution. It's just shift factor for the curve. If you plot it this way, Cp by T squared, right? So anyway, so that's just there. So that's what I wanted to do. And I wanted to go through this homework, which is about this stuff. So let me just shift over to that and get rid of this. So the homework is this paper. This homework, so the paper is by the guy Gruner that made the so this is the same Gruner that invented the idea of that gamma thing, right? So it's a short paper. It's from a long time ago. It's like 73. So this is around like the time superconductors people were interested, right? So okay, so anyway, he's got this Gruner constant here. That's the electronic contribution, right? You can ignore at high temperature. And he says the Einstein, right? And then this is the Einstein thing that I had in the notes, the same expression, right? So density of local oscillators, NL. NL's is the number of oscillators per atom, per atom in the crystal, or per atomic unit of the crystal. And the crystal here is called AL10V. Okay, so per AL10V, NL is how many oscillators there are per AL10V per formula unit, right? So there's 0.1, so there's 10% of the AL10V are an aluminum atom like this. It's a rattler aluminum atom. It's just shaking around, and that's giving rise to all the heat capacity, because he compares the heat capacity of this stuff, which is like 110, to like some other aluminum intermetallic, this Al9CO2, like aluminum cobalt, I guess. And that's 10. So it's 100 times bigger heat capacity than this. So this is a comparison heat capacity. And that's because of this rattler aluminum that's floating around in the lattice. Right. So it gives rise to this dependence. And then the function that's fit to it, so it's a perfect fit to the Einstein function. It's this function with this linear term added to it. So normally things wouldn't match up, and this is a perfect match. All right. And then he also takes the Bose-Einstein statistics, so like 1 over exponential this minus that is the probability of a free electron, and then he says that he can calculate the conductivity if he uses that Einstein, also the Einstein model. This comes from the Einstein model. So he uses the Einstein model, that Bose-Einstein's probability, to get his conductivity, and he gets kind of a perfect match for that too. And there's a temperature dependence is right. And this is a Debye temperature dependence for conductivity that we're not that interested in, but it's different. So there's a distinct difference between the two. So that's kind of what, it's just a short paper. He's just talks about this rattler atom and kind of, anyway, it's exactly like on the Einstein thing, right? So that leads you to some, so this is homework 11. Let me get these, that's that paper. So then this guy Cooper, right? So Cooper is another guy. All right, let me hide this. There. This Cooper guy, so he's taking this paper. So Gruner is the guy who invented this Gruner constant for the electron thing for heat capacity, right? And then he shows this plot, and there's like he says, well, the Einstein doesn't work over in this region. So once you get to, and this turns out to be like like this is, let's see, I can't read that, but so this is T squared is 18, so that's 9K. This is T. So that this curve ends like right around where this thing deviates. Right. So he's kind of gone further in temperature with the conductivity, and he finds out it fails there. So Cooper, this is the Cooper that invented a thing called Cooper pairs. Okay, so, and he won the Nobel Prize for the Cooper pairs. He was at the University of Illinois. So the idea is you have electrons, and then you have a lattice, and then somehow the lattice, because these are kind of plus, so that they move a little bit. The atoms want to get closer to the electrons, so they distort. So there's a lattice distortion. And then that lattice distortion, so electrons have spins up and down. If there's an electron that's spin down, so they can only occupy, so they can have 2 electrons per state, but they have to have opposite spins. That's like a quantum mechanic rule, right? So basically, if there's another electron near, so they both have the same charge, and this deviated that, somehow that makes this electron move over, like come closer. So the disruption of the lattice causes these things to pair up. And once they pair up, the way I understand it, they repel the lattice. So when you have a normal conductivity, you have the atoms, and sometimes the electrons hit the atoms, that leads to resistivity. That's a loss in energy. Otherwise, the electrons fly straight through. So if you don't have possibility of collisions, then you have an electron that can fly freely. You have no resistivity, 0. Right? So in this case, when you form this thing called a Cooper pair, this unit of the Cooper pair can move around freely. It never hits any of the lattice because it's got this association. The lattice itself has created the pair, and because of the lattice pair interaction, there's no resistance. So that's a Cooper pair model for superconductivity. So with a lot of math, like to calculate that. But basically, that's the idea. Like one electron is distorting lattice, that impacts another electron. Through that distortion, they're paired together. And once they're paired together, they can't hit the lattice. Then they can fly on the merry way. So the stronger the bonds in the lattice, the less of this effect. And the weaker the bonds, the more of this effect. So if you have an aluminum that's floating around in a hole with no bonds, that's an ideal situation to make a superconductor, a low temperature, right? High temperature, they don't understand, but this, they think they have kind of a grip on, right? So this idea is like, get a lot of atoms that are free in the lattice, and then you can make superconductors at like 10K. But basically, so there's a problem with engineering of it. But anyway, so this is the same Cooper. He goes in and he says like, so Einstein solids, this is Bose-Einstein statistics to say that the resistance is going to be proportional to that. And he's saying that came from that Gruner paper. And then it's kind of weird, like you have these 2 papers, and this guy won the Nobel Prize for this Cooper pair thing, and the other guy, the Gruner constant, I think it was too early to have a Nobel Prize, but he would have won it probably. So it's kind of like Nobel Prize guys talking about each other's work. It's interesting, I guess, in a certain kind of weird way. Anyway, so he goes through and says like what he was missing from it. I don't remember exactly, but he gets a perfect fit to that same plot. Like he goes back to Gruner's thing and he perfectly fits it by adjusting something about the interactions with the lattice. The vibrations aren't just single. When you get to higher temperature, there's some kind of anharmonic interaction going on. You can kind of read it and make some sense of it. But basically, he describes how to fix that problem. I'm going through these are the questions in here. So there's 2 terms in the first expression. So one is the Gruner term, and the other one is the Einstein capacity term. And then why does material display perfect Einsteins? Because these aluminums have basically, they're independent of the lattice, so there's no cooperative interaction. So deviations from Einstein because one atom moves and the other one has to move, but if they're independent, then you get perfect Einstein. So aluminums give it most of the heat capacity. So it's a perfect Einstein solid. This is like just in the notes is a bunch of Einstein temperatures. You can say like stronger bonds give a higher temperature. That's the main idea. And this thing has totally weak bonds, so it's got a really low temperature. And then equation 2 is this Bose-Einstein statistics to get the conductivity. And then Cooper fixes it. You can read Cooper's paper, but he talks about he adds in some other terms like anharmonic interactions. Whatever you can get from that is good enough. And then there's this other thing. So there's another paper along these lines. So I did that, and then this thing. So since this leads into superconductivity, there's like one about, and it's the same system. Like this is VL, aluminum 10 vanadium. And 0.1 means that's the free aluminums. But basically, the way they make it, they don't know it's 0.1. I think they just. So this is it's along the same lines. No one won the Nobel Prize here that I know of. It's showing like, so you put a magnetic field, so he puts on different magnetic fields. And he's got this transition, so you can measure the magnetic susceptibility. So a superconductor also has like zero magnetic, or there's a magnetic property to superconductors too. They repel magnets. Okay, so basically, I think that once these electron pairs are like flying around freely, they create magnetic fields, and then basically, so there's a magnetic field associated with this deviation of the lattice and formation of the Cooper pair that leads to superconductivity. If you put a magnetic field on, there's a cutoff magnetic field where you kill that, like that whole operation stops. So there's a transition magnetic field where you can kill superconductivity, and that's like a critical. So he's got different magnetic fields here. So he puts on different magnetic fields and at different temperatures. So his superconductivity with no field is at a relatively high temperature, 1K, and then like it shifts as he increases the magnetic field due to interference. This is kind of a verification of the Cooper pair idea. Like the magnetic field interferes with this deviation of the lattice thing. So he's looking at this. So that's what the question is here. It's like, what is the shows application of magnetic field can shift the superconductivity transition dependence on the temperature. Depends, and the heat capacity shifts too. So why is it superconductive? Because it's got these rattling atoms. It's the same thing. And then why the behavior depends on magnetic field? It's because of the magnetic field associated with the formation of the Cooper pair and this lattice deviation. I mean, that's about is what I have from it. You might get more if you read this. You can see the heat capacity goes through some weird shifts as you have different magnetic fields, and then basically the resistance changes. Like the transition to, so superconductivity is when it goes to zero resistance. So as you add more magnetic field, that shifts to lower temperatures. So you have to have a machine that can go to 0.1K to do this to begin with, right? So it's kind of a limited game. But once you have that, he even tells, like it's pretty easy to make these alloys. This thing, he tells how to do it. It's pretty simple. You just mix it together and let it anneal for 80 hours in an oven at some high temperature. And that's it. And then you have like a little puck you can put in with the DSC, or you can make a rod to measure the modulus or whatever he does with it. So he's going to make different size things to get these different measurements. For resistivity, they make a rod. He says in this like what he does. So it's not hard to make the material. It's just you have to have this squid machine. You have to have some big, but we have one of these in the department. If anybody's interested in doing this, you can do it. It's like basically we can do this here, but I don't know, again, like it isn't a field that people are really doing much with right now because they never, like this is what, 2012. So people are still doing it, but I think it's kind of left over. Like there aren't people really doing superconductivity now. Like the Los Alamos, so they were doing it before. So we have like Dalu Shi, for instance, in our department, is like one of the leaders in superconductivity. And he was at Argonne Lab, and I think he published 200 papers there on this, on superconductivity. And then like now he's not doing anything like that. Now he's doing like biomedical something, windows that heat up and things. There's nothing to do with this. And he says, he claims he's doing polymers now. So basically like everyone has run away from superconductivity, you know. So it's still kind of a main course in materials somehow, you know, because so much money was put into it. I think it's still really, I mean, like huge amounts of money was put into it because if you could make transmission lines that had no resistance, that would be a pretty big deal, I think. So that was the idea. Like they were going to have transmission lines and the cooling, like they could do it almost at room temperature, things like that, you know. And then, but the problem is material is so brittle, you can't make anything with it. So once you make these intermetallic compounds, they're super brittle. So if you try to make a wire with it, it just breaks. So you can it can run a couple of days and then it breaks, you know. So it's like kind of useless. You put a lot of money into the alloy being made. So anyway, so but for things like an NMR, they use this, like it's pretty common to use it, you know. Anyway, I think that's about it. I kind of did that faster than I thought, but that's all right. Any questions or anything? It's a lot of stuff. Like I think you just got to look at it, figure out. This paper might help because it shows like an actual application of the Einstein equation and where kind of where it fails. Like, and also, so it's just the discussion of it. I think if you look at how he's discussing it, it will help a little bit because it puts it into a context of a specific problem that he's looking at. So, so hopefully that's all right. And I don't know, that's about it for today. I think the Dubai is a separate subject, you know, so I don't really want to start talking about that because it kind of gets into this. Oh yeah. So like, is there any time you guys like? There's a so the density of states, you can measure that. There's an instrument called Brilliant scattering, and there's an instrument that does that in the department. That sometimes they take this class to look at it. I don't know if you guys have any time that's free though. Like after this class, do you guys have time free or? Oh, okay. All right, maybe a different time. I don't know when. I don't know. I see. Oh, so it's composites after this? I see. Oh, okay. All right. Okay. Oh, that's pretty interesting. Yeah. Well, I used to teach it, but I kind of gave up. During COVID, I gave up on it. But that's pretty interesting. So it's just a lecture class. Yeah. Because I did it, it was just lab, no lecture. Yeah. People liked it, but it was a lot of work. It was like lab reports. Actually, a lab report a week. It was a lot. But anyway, so you guys are all polymer people or? Yeah. All right. I know what you are, but yeah, yeah. You're superconductors. All right. So, all right. Well, that's pretty good. Yeah. Why don't we quit there? I think it's good enough. Any questions? I mean, it's a lot of stuff. I don't know. It's like the semester is getting spinning by, you know, and we need to, like, that's a picture of a DSC to measure. So you see that in the characterization class, right? Yeah, so that's kind of the DSC. This is a curve. This is actually a polymer curve. Like glass transition. This would be like a water bottle. I don't have one here, but PET. So when you heat it up, like it's clear, it's non-crystalline when you have it because it's been extruded quickly and cooled. Then when you heat it up, you go through glass transition. So there's a difference in heat capacity, but there's no enthalpy. These are enthalpies of formation, the area under the peaks. And then as you heat it up, it'll crystallize, it'll turn white. So this is the crystallization going on. So you see it says, it'll always say like endo, usually it says endo, this is exo. So yeah, usually it's, no, this is exo down, so upside down. Yeah, so you gotta be careful. No, I mean, on the machine, you can push a button that says endo up or endo down. Usually it's endo, not exo. But anyway, this is endo down, which means exo down, so endo up. So anyway, it's giving off heat, I guess. Well, it's crystallizing here and it's melting here. So melting is going to require heat. Crystallization is going to consume heat. So it consumes, crystallizes, turns white, and then it melts again. Be like I think it's 110 or something for PET, 120, something like that. Then it's a liquid over here. So the heat capacity of the glass is lower than the crystal, and the crystal is lower, should be lower than the liquid. So this is, so heat flow on this, so you have, so you're putting heat into it. This is watts of heat that you're putting into it, but the heating rate is linear. So the watts would be like, the watts would be Q and then dQ dt. So like energy per time is watts. So this would be dQ dt. And if you multiply it by a constant heating rate, dt dt, d temperature with time, or divide by that, then you get dQ dt. So that would give you like heat capacity. So it's really heat capacity over here. If you multiply it by the heating rate, which is constant. So it's just a constant times the watts that you put in is the heat capacity. So the number is like the liquid. The glass has a lower heat capacity. So because you have more motion, more translational motion, you get more heat capacity when you get to liquid. Basically, it's going to be a step thing with heat capacity. And the top one would be like polystyrene, except they've shifted the TG to be the same, but polystyrene doesn't crystallize, so it's just a glass or a solid. Solid will be low temperature or liquid. I mean, it's a liquid or a solid, but so anyway, so the polymers are good. They have nice, pretty clean. If you do a metal in this, it's just a spike. There's no peak. Like because the polymers, depending on the thickness of the polymer, you have crystals that are like this, but some of them are really thin and some of them are thick. So the thick ones have a high melting point. And the thin ones have a low melting point. You have, instead of having a spike like in a metal, you get this broad thing. We have all these different crystal thicknesses that govern the temperature that melts it. The crystallization is crystallizing different thickness crystals to get a broad peak here. Metals, you won't see a glass, actually, unless you shoot the molten metal at a wall. You can make a glass, but you won't see that in a DSC. The cooling rate would have to be so fast, right? So polymers have more to look at in a DSC, I think. But you use indium or some metal to standardize the temperature scale because it's just got a spike and it's just exactly where. So indium and naphthalene, sometimes you use like mothballs. They have spikes here, so you can calibrate. So usually use indium and naphthalene. You have at least 2 points to get the scale right for temperature. So, and then you also know from the mass of the indium and the naphthalene you put in, you can just get this scale right too. So you kind of calibrate the thing with standards before you run it. And then that's kind of the workhorse for thermodynamics, actually, like for measurements. So yeah, in the paper he's got, anyway, so hopefully you can kind of go through this a little bit, but it'd be good to go through, well, it asks you to go through, it asks you to derive this equation. So you're gonna have to go through this thing. That's the point, it's like go through this mathematically and get that answer. It's possible to do, and I gave you the hints here. Like you need to know that if you know the z is that, and then you take the derivative of that, you get this. So this is that. And then you know dz by z is d ln of z. And you can show that, but that's basically how it works. And then going from d ln z to this is kind of a step. Like you have to take this function So you have that function, and ln of that function is just an argument. So anyway, somehow you can get this from that. This step is the hard step. I guess I put down what z is, and then d ln of this. So ln of the exponential is the argument, but ln of 1 over the 1 minus isn't. So that's the argument part, gives you this lead term. And then the other part, the 1 over that, gives you this term if you figure it out. And then once you have that term, this is just shifting things around, like divide by either minus h nu e over kt gives you this thing directly, and there's a prefactor of that goes there. That the only step that's bad is like that to that. It's doable, like you can do that. So it asks you to do that. And this is for 1 vibration, you have to multiply by 3 for x, y, z to get the final function. It's in that paper. Whatever that is, like this. That's not it. No, it's a disappeared here. Like that paper, the CE equation. The gamma part, I'll go over that some little bit of detail later, but we have it. We already have it now. Anyway, I think that's the. It shouldn't be too bad. I looked at it and looked, it's just a 3-page paper, so it isn't much to do. It's just it's a little complicated what's going on. So hopefully you can kind of get that. I think if you can get the Einstein, so there's 2 things you need to get is the Einstein and the phi. So the Einstein's the simpler of the 2. But basically it's also the groundwork for everything. So it's good to get that as good as you can get it. And then it'll be easier to go on to the other. Anyway, so we're out of time, I think. Why don't we quit there? Yeah. No.